Okay, then the particles are identical. That is proton proton or neutron neutron scattering. There is one important, very important difference between the scattering of identical nucleons and the scattering of different nucleons, neutron proton scattering. The previous videos we have learned the neutron proton scattering. This difference comes about because the identical projectile and target nucleons must be described by a common wave function. Both the particles are identical. If the both particles are identical, we cannot differentiate them. Which one is projectile and which one is target nucleon. So we use describe by a common wave function. Because nucleons have spin half, their wave functions must be anti-symmetric with respect to interchange of the nucleons. If we again consider only low energy scattering, so that L equal to 0, interchanging the spatial coordinates of the two particles gives no change in sign. Thus, the wave function is symmetric with respect to interchange of spatial coordinates and must therefore be antisymmetric with respect to interchange of spin coordinates in order that the total spatial time spin wave function be antisymmetric. Therefore, only singlet spin states can thus contribute to the scattering. Consider this figure, which represents the scattering of two identical particles in the center of mass reference frame. Okay. This represents scattering of identical particles in the center of mass system. One particle emerges at the angle theta and the other pi minus theta. Because the particles are identical, there is no way to tell which particle emerges at which angle, and therefore we cannot distinguish the two cases shown. So in the case of identical particle, we cannot distinguish which one is target, which one is project after the scattering. The scattered wave function must therefore include contributions for scattering at theta and at pi minus theta. When we square the scattered wave function to calculate the cross section, there will be a term proportional to the interference between the parts of the wave function that gives scattering at theta and at pi minus theta. This interference is purely quantum effect. Let us first consider scattering between two protons, the pp scattering. The wave function must describe both Coulomb and nuclear scattering because proton has charge, and there will be an additional Coulomb nuclear interference terms in the cross section. The differential cross section is found as d sigma by d omega e square by 4 pi epsilon 0 whole square 1 by 4 t square into 1 by sine power 4 theta by 2 plus 1 by cos power 4 theta by 2 minus cos eta natural log tan square theta by 2 by sine square theta by 2 cos square theta by 2 minus 2 by eta sine delta 0 into cos delta 0 plus eta natural log sine square theta by 2 by sine square theta by 2 plus cos sigma delta 0 plus eta natural log cos square theta by 2 by cos square theta by 2 plus 4 by eta square sine square delta 0. Here T is the laboratory kinetic energy of the incident proton. Theta is the scattering angle in the center of mass system. Delta 0, the L equal to 0 phase shift for pure nuclear scattering, and eta equal to E square by 4 pi epsilon 0 H cross C into B power minus 1 is equal to alpha by beta, where alpha is the fine structure constant with value nearly 1 by 137, and beta is V by C is the dimensionless relative velocity of the protons. Beta is relative velocity. The six terms in bracket can be readily identified. First term, the sine power minus 4 theta by 2 is characteristics of Coulomb scattering, also known as Rutherford scattering. Second term, the two protons are identical. We cannot tell the case in which the incident protons uh, comes out at theta and the target proton at pi minus theta. In the center of mass system, from the case in which the incident proton comes out at pi minus theta and the target proton at theta. Thus, the scattering cross-section must include a characteristic Coulomb Rutherford term sin per minus 4 pi minus theta by 2 equal to cos per minus 4 into theta by 2. The third term, this term describes the interference between Coulomb scattering at theta and and at pi minus theta. Fourth and fifth term results from the interference between Coulomb and nuclear scattering. Sixth term is the pure nuclear scattering term. The limit E tends to 0. If it is pure nuclear scattering, only this term survive. Delta 0 is the only unknown in the above equation. We can measure the differential scattering cross section as a function of angle and extract delta 0 from the best fit of the result to the equation, and it is reduced to that delta 0 equal to 50.966 degree at equal to 3.037 MeV. From many such experiments, we can observe the dependence of delta 0 on energy. And the proton scattering length uh, A equal to minus 7.82 plus or minus 0.01 femtometer. R0 is calculated as 2.79 plus or minus 0.02 femtometer. The scattering length is a parameter used in analyzing nuclear scattering at low energies. As the energy of the bombarding particle becomes very small, the scattering cross-section approaches that of an impenetrable sphere whose radius equals this length, also known as scattering power. For low energy scattering, scattering cross-section 4 pi a power a square, where a is the scattering length. It is however important to note that A is negative, suggesting that there is no proton-proton bound state. That is, the nucleus 2He does not exist. Okay. The neutron-neutron scattering should be free of the effect of the Coulomb interaction that made the analysis of proton-proton scattering so complicated. Here the difficulty in experimental one, although beams of neutrons are readily available, targets of free neutrons are not. Measurement of neutron-neutron scattering parameters therefore requires that we use a nuclear reaction to create two neutrons in relative motion within the range of each other's nuclear force. As the two neutrons separate, we have in effect a scattering experiment. Unfortunately, such reactions must also create a third particle. The experiments that have been reported include the breakup of a neutron following capture of negative pi meson. Negative pi meson plus 2H gives 2 neutron plus gamma, and following neutron scattering, neutron plus 2H gives 2 neutron plus proton. The analysis of these experiments gives neutron's parameters A equal to minus 16.6 plus or minus 0.5 femtometer, R0 equal to 2.66 plus or minus 0.15 femtometer. As with the proton-proton interactions, the negative scattering length A shows that the two neutrons do not form a stable bound state. Okay. Next, we will see the properties of nuclear force.